That would be helpful. Hello and welcome back to Calculus 1 on this gloomy Saturday morning, right? First and second derivative tests. Functions of whatever kind, right, are there to model our reality. We use them to build devices, to describe phenomena, to understand the world around us, and so on. So, in some cases, we would like to know if the function is increasing or decreasing, and then certain things about concavity and so on. And this is where these tests kick in. And eventually, we're going to use this in the next lecture to graph function by hand. So right now, you probably memorized the graph of ln x and e to the x, but what is the graph of ln x squared? What is the graph of ln squared x? What is the graph of sine x squared, or 1 minus sine x, and stuff like that, right? You'll be able to graph all of those without calculator. That's usually what I say, right, in case of an emergency. Graphing by hand, right? Anyway, the first and second derivative tests will tell us things about the function. If you take a look at any stock graph which displays the variation in stock price, you can extrapolate, right, the function, and then you can talk about increase and decrease. So let's say they all look like this because they're simulating heart attack every time you look at it. You can just smooth out this curve, let's say, even though there is a huge drop over here now. So I'm just going to fix that like that. There we go. So it's more representative of the graph. So the black graph is the reality, right? Because this is money, this is time. But then the red graph is the one that you fit through. And when you fit the graph through, you want to analyze and understand that, okay, I am on the upward trend, so I'm not losing money, so, right, because as you can see, this part of the function here is increasing, right? So it's increasing in time. As you go to the right, the y values are growing. So if I am to just now take it out of the applied setting and just put an arbitrary function, what we see is that we have a relative max, right? We also have a relative min, and those are where you have your slopes to be 0, right? But then what we are concerned with today is that there is a piece from negative infinity to whatever this value a is, on which the function is increasing. Then you have this other part from a to b, where the function is decreasing, and then in blue again, from b to positive infinity, you have another increasing piece. So there is an increase, increase, and let's do red for decrease. Now, obviously, it follows our visual cues, right? The function is going up, so you're walking uphill. You always walk to the right. That's the way the positive values in x go. So you walk uphill, downhill, uphill. So increase, decrease. So these concepts are not new to you. You know exactly what it is. So what we want to learn, the mathematical calculation, right? Calculation that will give us these intervals as a result. So we don't have to look at the graph. We can just take a look at the function f of x and then be able to calculate these things. In some cases, it's more, well, first off, it's obviously more precise than just, staring at the graph, especially if decimals and irrational numbers are involved. So let's take a look at the first derivative test procedure, theorem. First derivative test, I abbreviate that with the FDT, first derivative test, right? So we're going to use FDT, and this is what it says. If f prime at a value c is less than 0 on some interval a to b. Could be open or closed, it doesn't matter. But usually open. So if f prime of c is less than 0 on AB, then f of x is decreasing on that interval AB. Next one. If f prime of c is larger than 0 on interval AB, then f of x is increasing on AB. If f prime of c is equal to 0, then c is a critical point, and you know that that one can be min, can be max, and can be, I'll just put purple question mark here for inflection point, but inflection point, we are going to learn inflection point in our second derivative test, so you don't have to worry about it now. So we are learning it today. So this box here is your first derivative test. And it's very simple, right? All you get to do is check values, right? Plug some numbers into first derivative. So first function that we are going to try this on is the good old x squared. You know everything about x squared, so we're just going to verify, right? You already know the interval on which the function is decreasing, interval on which the function is increasing, so but we're still going to do calculation. So we start by f prime of x is equal to 2x, and we set this equal to 0 to force to find critical points, right? To find critical points. So x equals 0 is what we call critical number, right? And then we plug that to get the y value. So f of 0 is 0 squared, which is 0. So now we have 0, 0, which is critical point. So none of this should be new, because we did this in 4.1 to find min and max. So there's nothing new so far. Here comes the new stuff. For us to use the first derivative test, so this is where the first derivative test starts, we partition the domain, in this case from negative infinity to positive infinity. We partition the domain at critical numbers. So I'll write here like this. We partition the domain using all critical numbers and vertical asymptotes. We don't have any now, but we will have later. And vertical asymptotes. So your domain for any polynomial function, you know that from pre-calc, is all real numbers, from negative infinity to positive infinity. Our calculation gave us critical points and certain, right, certain other, what do you call, certain other functions will have vertical asymptotes as well. So we put these barrier walls, right, which create now these AB intervals. And now you pick test points. So you can pick -1, 1, you can pick 2s, you can pick whatever it fits, whichever number fits inside each partition. So these numbers here are your test points C. And those are the ones that you see. Remember how you had in the definition f prime of C? Those are your C's. You pick those C's, one in each partition. So now, f prime of a C, which is a -1, is going to be 2 times -1, which is equal to -2, and that's less than 0, and by our first derivative test, meaning f of x is decreasing, yes. So you put the arrow going down in this partition, right? You put the arrow going down on the partition. Then you go back and you calculate the second test point. So that's going to be 2 times 1 is 2, which is bigger than 0. And from our calculation, f of x is increasing, exactly. So that's going to be green, and it's going to go up. Can you tell me what you get for free from this calculation? What information are you getting for free? Earlier we had to struggle a little bit to figure it out, but now it's just obvious. What will you get for free? We were not calculating it, but it just pops out. So something on here I never mentioned in this problem. We used to calculate it before, and it was a little bit annoying to figure out what's what, but now you get it for free. What is that 0, 0?
It's the minimum.
How do you know?
Oh, it was going down.
Yes, look at the green arrows, right? You look at the green arrows and you see that it's going down to 0 and then it's bouncing up. It's a minimum. You get that piece of information now for free. You are not calculating, right? Because you did calculate point to the left and point to the right, right? But this calculation was there to tell us the intervals of increase and decrease, and you get all of your min and max values free of charge right away, which is awesome, right? Now let's write the answer to the question. The question says, find the intervals of increase and decrease, right? You have a pretty graph, right? But you want to actually provide the answer that you box and not lose points. So, answer. F of x is, yes, is decreasing on -infinity to 0. And then underneath, f of x is increasing on 0 to infinity. And then you box that. So this is what we have. This is what we get, which is awesome. Does this make sense? Of course, you know that the right looks like it's a parabola graph. You see the minimum, you see the decrease, you see the increase, so everything is good. Next example, 1 over x. 1 over x. So, okay, let's do 1 over x. Our first derivative is -1 over x squared. When you set this equal to 0 and you cross multiply, you get that -1 is equal to 0, and then you say, well, it's not equal to 0. So this means no solution, which means no critical number, which means no critical point, which immediately means no min-max. Wow. So this is the logic that you follow from this calculation, right? It starts at a derivative that -1 equals to 0, which has no solution, which means no critical number, which means number. So no critical number, no critical point, no min, no max. Great. Well, are we doomed? No, we're not doomed. We still do first derivative test. First derivative test says you get to partition on critical numbers and vertical asymptotes. Do we have a vertical asymptote? Yeah, we do, right? Vertical asymptote at 0. So when I do my partition for from negative infinity to positive infinity, I partition at 0, which is the vertical asymptote. I still pick my C values, which are, what do you call it? Test points, right? And now we calculate our first derivative at those test points. So f prime of -1 is -1 over -1 squared. You're plugging it in the first derivative, and what you get is -1 over 1, which is -1, which is less than 0, which is decrease. So this implies f of x as a decrease. Then we have f prime of 1, the other test point. -1 over 1 squared is still -1, is still less than 0, which means that f of x is still decrease. And we draw another green arrow. Now look at the orientation of these two arrows. Right? Do we see that there is no min there? There is no max, right? Because for max you need up and down, right? For min you need down, up. They're both down. But we already know there is no min max because we were not able to find any critical points. This is called mathematics. It has to click. It has to click. So now we write the answer. F of x, you can say equal 1 over x, right, is decreasing on negative infinity to 0, union 0 to infinity. Is decreasing on the entire domain. And that's the answer. That's the answer you provide, and you walk away. Now, you all know the graph for 1 over x, and you know that this fits. Right? That's the graph. We see that the graph is constantly decreasing, right? It goes up. So it's decreasing on the first shot, it's decreasing on the second. So that's what we have. So it's just decrease across the board. Great. Let's take another introductory easy function, and then we'll take a look at some spicier stuff. How about we look at e to the x, right? So f of x or y equals e to the x. All right. So what's the derivative? Set equal to 0. What is x? Well, if you ln both sides, you get ln of 0. ln of 0 is negative infinity, so no solution. No solution means no critical number, means no critical points means no min max. So this is what we have for so now great. How about vertical asymptotes? Do I have any vertical asymptotes for e to the x? And the answer is no, we don't, right? So we have no min-max, no critical points, and no VAs either. Can you do first derivative test? The answer is yes. Because you don't get to partition domain. Entire domain is one partition. And you just pick one point anywhere. So, your domain is always there because there's always a function, right? If you have critical numbers, you get to subdivide it. If you have vertical asymptotes, you get to subdivide it. If you don't have any of those, then the entire domain is one big partition, right? One big partition, the entire domain, and you just pick a value. In this case, from negative infinity to positive infinity, you pick anything. I'll pick 0, right, as my C. So I'll write here in blood, we have no critical numbers and no VAs, no vertical asymptotes. So the entire domain is one partition, and we pick one test value, and then we do first derivative test. So now my value is 0, and I go and I say f prime of 0 is e to the 0, which is equal to 1, which is bigger than 0, which means that f of x is increasing. And you get to write the answer now, which says f of x equals e to the x is increasing on negative infinity to positive infinity. And that's the answer. Does this make sense? Of course. You know what the graph for e to the x looks like, right? It's always increasing. So we haven't reinvented the wheel or anything. We just showed that the calculus that we do fits this. Now, do we do first derivative test for functions that we are certain what they have? The answer is no. We want to do this on some more complicated, dare I say, annoying functions. So let's take a look at the homework and see what they have. Here's a beautiful example, 47. It says f of x is equal to x times the square root of 4 minus x squared. Right? Cool. Do you know what the graph for this looks like? No, right? You don't. But can we find the intervals of increase and decrease? Can we find intervals of the increase and decrease using calculus without the graph? The answer is yes. First order of business, first derivative. This is what? Product and a chain, right? Now, if you know logarithmic differentiation, this is the time to use it, right? Because you want the factored answer, because you'll be setting this equal to 0. So your logarithmic differentiation in this case saves your life. I mean, not saves, it saves your time. If you use product rule, you are still okay. So copy the first times the derivative of the second. So that's going to be 2 square root of 4 minus... Oh, no. Huh. I said let's do logarithmic differentiation. So x square root of 4 minus x squared. So you copy. For logarithmic differentiation, you always copy the problem as is, right? And then we go in and we say 1 over x plus 1/2. Downstairs is 4 minus x squared. Upstairs is negative 2x. And then these 2's will drop. So the f prime of x is just x square root of 4 minus x squared, and in parentheses over here 1 over x minus x over 4 minus x squared, and that's what I have. So now I set this equal to 0 because I want to find the critical numbers. I want to find critical points to find where to partition, right? Now, there are also some domain issues that we want to discuss, but we'll get there. So what are my values? Well, guys, I have 3 factors. 1, 2, 3, right? I have 3 factors, which means I go x equals 0, x equals, square root of 4 minus x squared equal to 0, and 1 over x minus x over 4 minus x squared equal to 0. So these are equations I have to solve, and some of these equations are going to give me numbers that I use for partitioning. X equals 0, that's already done, right? Now, over here, square both sides, you get 4 equals x squared, x equals plus minus 2. I got another 2 of these, right? The third one, so these are all separate. Separate them with the blue line here. This one is, you make them equal first, right? You move one term to the other side, and then you cross multiply. You get 4 minus x squared is equal to x squared. And when you put in these x squared together, you get 4 equals 2 x squared. So x squared is equal to 2. And finally, x is equal to plus minus root 2. So I have 5 different numbers. Now, there is something interesting happening here, because we did not talk about the domain of this function yet, right? So you are always tempted to go from negative infinity to positive infinity. But I'm going to ask you right now, how's your function doing if x is equal to 3? Your original function f of x. How's it doing when it's 3? What's happening under the root? Right? Are you getting 4 minus 9, right? And 4 minus 9 is negative 5. And what's the square root of negative 5? Not real. So we have domain issues here. Domain is from negative 2 to positive 2. You see that? So now, if I am to do the partition, I'm not doing the partition from infinities. I'm doing the partition between negative 2 and positive 2 because the domain of the function requires it. Now, I still have a partition at 0 because of this, and I have the other 2 partitions as well at negative root 2 and positive root 2 because of that. So this has a lot of partitions in it, right? It has a lot of partitions, so we use them all. And now is your job to pick test points in each one of these regions and test them. So we go and we say test points. Well, definitely negative root 3 would work fine. Negative 1, positive 1, and square root of 3. Because square root of 3 is less than square root of 4, right? Square root of 4 is 2. And square root of 2 and square root of 3, right? 2 is smaller than 3, so root 3 must fit in. So that's perfect, right? So we're going to use these 4, right? These 4 critical, these 4 test values. I mean, you can't go wrong. Even if you messed up on your domain and not paying attention, you're just wasting time, right? You're not going to be dead wrong on a problem, because, right, if you go negative infinity, what test point you're going to pick between negative infinity and negative 2? You're going to pick negative 3, right? Or negative 5. And the same thing on the other side. You'll pick 3 or 5 or 10. When you try those, it will not work, right? Because when you plug them in a first derivative, you have this to compute still, right? And it will fail, right? It will give you complex numbers. So you would see that something is wrong, and you would know that you are out of bounds, out of the domain. So it is great to know the domain on the start of the problem, and then you don't waste your time with values that you're not supposed to waste your time with, right? But if you don't, well, right, you still get to do these things. So now we do our first derivative test for our first point, which is negative root 3. So f negative root 3, f prime. F prime is, so x, that's going to be negative root 3, times, and now we have 4 minus, so square root of 4 minus negative root 3 squared, and then we have the big parenthesis, 1 over negative root 3 minus negative root 3 over 4 minus negative root 3 squared. I understand, yes, this is annoying, right? But such is life. So negative root 3 square root of 4 minus 3, and then negative 1 over root 3, minus and minus gives me a plus, root 3 over, and this is again 4 minus 3 in denominator, because when you square the root it just goes away, and the negative goes away too. So what do I have? I have negative root 3 times 1, because 4 minus 3 is 1 and root of 1 is 1, times negative 1 over root 3 plus root 3. Now, you can punch this in the calculator and get the, number down to the 7th decimal. No one cares. You only want to know if this number is positive or negative. If it's positive, increase. If it's negative, decrease. No one cares if it's negative 1 or negative 10 or negative 100, right, to the 7th decimal. All we care is positive or negative. And look, I just go negative number times positive number times another positive number, because, right, the fraction is smaller than the big piece, and this is positive. So when you get them together, so the whole thing is equal to a negative number, and the negative number is less than 0. So the first one over here is a decrease, and we put the green arrow going down for a decrease. Rinse and repeat for negative 1, rinse and repeat for 1, rinse and repeat for root 3. You don't get to claim symmetry all the time. They do not alternate all the time. Didn't we have for 1 over x decrease followed by a decrease? They will rearrange themselves in any way they have to in order, right, to follow the function. So rinse and repeat for negative 1. F prime of negative 1 is negative 1 root of 4 minus negative 1 squared and then 1 over -1 minus -1 over 4 minus -1 squared. So this is going to be -1 times √3 times -1 plus 1/3. Again, I'm going to do sign analysis. I'm not calculating this. There's no reason. Negative times a positive times a negative is equal to a positive. So we have arrow up. And now we get to do f primer 1, which is 1 times 4 minus 1 squared, 1 over 1 minus 1 over 4 minus 1 squared. Compute as much as possible. You don't even have to worry about 1. This is going to be √3 times 1 minus 1/3. Do we see that all of this is positive? So when you multiply two positive numbers, you get another positive. That's larger than 0. So we have a green arrow up. And see this? This is why you can't just go and say, I'll alternate, right? Because you have decrease, increase, and then increase again. And the next one will be decrease again. So again, they arrange themselves the way they have to. So we have this. All right. Give me 1 second.
Box.
I'm not sure that you need this.
No, there's a flag in there. And okay.
No. Give me that. Yeah. Give me that. I'll see that.
I think I'm missing something.
No. You have it.
Oh yeah, that was a big box.
She recruited me.
We'll be downstairs for lunch.
Where's the chicken?
You guys
I
done?
think I'm kidding.
There's like nothing supposed to do. We've been sitting in classrooms, bouncing from classroom to classroom, so we look busy.
Okay.
Like 3:10 on the dot.
Yes, well, earlier, hopefully. √3, that was a quick interruption for a conference we're having. So, for both of them, actually. One is covering here, one is covering there. Anyway, √3, so that's going to be the same calculation, except some of these minus signs are going to be gone. So we have this, we have 4 minus √3 squared, 1 over √3 minus √3 over 4 minus √3 squared. So we calculate as much as we can. We leave the √3, and then this is going to be square root of 1, which is positive 1. And then we have 1 over √3 minus √3. So now √3 is bigger than 1 over √3. So we are going to have positive, positive, and this is going to be a negative. So altogether, positive times negative is a negative, which is less than 0. And then we are going to have our green arrow down. Now, what did we get for free?
The local min.
We got the local min and max because at negative √2, you see there is a minimum because the arrow goes down and then goes up, right? So it's a minimum. And on the positive √2, you have a maximum. So these are the, this is the analysis that you can do. And, in my never humble opinion, it's cool, right? So we have answer. This is what you have to provide. F of x is decreasing on, and then just look at all of the arrow down. We have -2 to negative √2, -2, negative √2, union √2 to 2. F of x is increasing on negative √2 to 0, union 0 to √2. And that's the answer that you box. And then you go and you say the stuff that you got for free, right? X equals negative root 2 is a minimum. X equals positive root 2 is a maximum. And then I'll just say here, as in blue, get Y values. So you go f of negative root 2, you just compute the original equation, right? So, is this function easy? Do we know what this function looks like? The answer is no, we don't, right? But we are able to say with a great precision what the actual values are for intervals, right, for increase and decrease. Now what I'm going to do is I'm going to go to Desmos, right, and graph this function to verify our calculations. This is the beauty of chapter 4, right? You get to graph and you get to look at it with your eyes, right, and make sure that what you calculated actually shows up. So we have x times the square root of 4 minus x squared. And look at that. A little squiggle. Whoop, right? Make it larger. And you can see the square root of 2 is about 1.4, right? 1.4. This is 1.4 over here. 1.5 is the in the middle, right? So if you go up, there's a max at root 2. Here is the end at 2. Remember how I said there's no domain. You try 3, fails, right? Now, you will know how to graph the whole thing by hand in the next section. And this calculation will be a part of it, right? So the next section is 13 different things on a shopping list for us to calculate, and then we're able to compute the entire thing by hand. So this is what we have. And now, as I said, please use technology. Guys, when I was taking this class, YouTube didn't exist. YouTube did not exist. I took this class 4 years before YouTube started, right? So this class for me was in 2002, all right? I took Calc 1, 2002. For the second time, so I took it already there, but it doesn't transfer credit to the US and so on. So I was just sitting bored learning English, actually, because I didn't learn math there. But I took Calc 1 in this country. And none of this stuff existed, right? The internet was you dial the phone and connect, right? And you pay per hour. That's, right? That was the internet at that time. And if you had a DSL connection, blazing speeds of, of half of a bit per second, right? So my speed right now at home is 3,000 times faster than what I had when I was taking this class. And YouTube did not exist as a concept either, right? Or maybe it did, but right, it came up 4 years later. You have the tools, right, to learn it on YouTube, to learn it, right? You can watch the lecture again. And the benefit of the website like this, where you graph the function and you say, aha, is my answer actually 100% reflection of what this is. So now the question is, right, do you know how to find the derivative, right? That's all, right? Because you're taking the first derivative and you just plow through calculation. That's all it is, right? So this is your first derivative test. Now I know how much you love and appreciate trig. So we are going to do a trig question for the first derivative test. and then we're going to do the second derivative test. So let's take a look at which problem should we look at? Should we look at 31, 32, 33, 34? Let me make this larger so you guys can. Can I make this larger? Zoom options, nice. Boom, 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 boom. 200. So here they are, 31, 32, 33, right here. Which one should we take a look at?
33.
33 with the 3 cosine 3x. Solved. And I think that my other lecture for my other Calc 1 class on the stream had maybe 31 or 32. So you have an extra trig example if you watch the other lecture. So f of x is 3 cosine 3x, and they want us to focus on a domain negative pi to pi. We know that cosine goes forever, right? But that's just going to create infinitely many critical points, right? So we're going to chop it off at negative pi to pi. Great. Now you technically should know what this graph looks like because you guys, right, took the trig course and there was a graphing there which says this is your A, this is your B, and now you can graph it, right? But in calculus we are bypassing all of that, right? We're just going to do the derivative, f prime of x, which is going to be negative 9 sine 3x. Right, the chain rule kicks in and the 3 multiplies 3 in front. And now we're setting this equal to 0. So we have to solve sine 3x equal to 0. So when is that happening? Now I'm going to draw sine x from negative pi to pi and ask you how many times sine function hit the 0. And the answer is it hit 3 times, right? Now, pay attention. Here is a scoop. You are going to say that the 3x is equal to negative pi, 3x is equal to 0, and 3x is equal to pi. Because your angle is not x, your angle is 3x. So now you have to solve these equations and you get x equals negative pi over 3, x equals 0, and x equals pi over 3. Right? So those are the 3 that you worry about. Then we don't have any vertical asymptotes, right? So no VAs because it's a cosine. And now we do the first derivative test. We partition. Remember, we have the endpoints, right? We have the endpoints because those endpoints are your pi's. So negative pi and pi on endpoints because that's what's chopping our domain off. And now we have the 0 in the middle. And then we have pi over 3. So negative pi over 3 and positive pi over 3. And we are supposed to choose test points. Now all of my calculations are at 3x. So I'm going to choose test points that have multiples of 3 in denominator to make it easy. I can't really pick 2 pi. I can't really pick, right? I can pick pi over 2, but that'd just be annoying. So what I'm going to do is I'm going to pick negative 2 pi over 3 and negative pi over 6. So multiples in denominator, they will cancel the 3, right? Multiples of 3 in denominator are canceling the 3 for 3x in the calculation. So pi over 6 and 2 pi over 3. So now we calculate the first derivative, negative 2 pi over 3, and the derivative was negative 9 sine 3x. So negative 9 sine 3 times, and now you have your negative pi over 3, right, to worry about. So that's negative 9 3 and 3 will cancel. Uh-oh. Uh-oh. Somehow I missed these solutions. How did I miss these solutions? Guys, I'm getting, do you see that I'm getting sine of negative 2 pi? That the negative goes out and kills the negative? Sine of 2 pi is 0, right? Which means it's another critical point. How did I miss that? They're hiding somewhere. So I have to change this into a partition now and pick other points. I have to pick more points. So negative pi over 6, negative 2 pi, negative 3 pi over 6 is negative pi over 2. Negative 4 pi over 6, negative 5 pi over 6. Holy nightmare. Okay, let's see. So now if I have negative pi, 5 pi over 6, over here, that's going to be negative 5 pi over 6. Now this cancels, and it becomes, and the minus and minus cancel. So it becomes 9 sine of 5 pi over 2. And sine of 5 pi over 2 is, when you do this, forever, that's pi over 2, 3 pi over 5 pi over 2 is 1. So this becomes 9 times 1, which is 9, bigger than 0. So we have an increase on the first shot. Now, the good thing about sine and cosine, right, it's going to be wavy. So you can immediately now go and just put up and down, up and down, up and down. But let's do another one. F prime of negative pi over 2. F prime of negative pi over 2. And that's going to be negative 9 sine of 3 times negative pi over 2. So minus and minus are gone. So that's 9 sine of 3 pi over, over 2. So this is 9 times negative 1, which is less than 0, and you see an arrow going down, arrow going up, arrow going down, arrow going up, arrow going down, and you got your min and max values for free. You got your min and max values for free, and you have all of yours. You didn't ask about the question. Let me get the dragon out. You know. Well, if I push it, small, tiny, you know what I'm talking? They're doing the fire. I know you need fire, but oh, you said you cleaned the fire. I heard you ate spiders, and I know you do, but during my time, how many? A lot.
You see it, right? Yeah. So what is type of light? Dark, moist places? Yeah, I just see it.
People say 3. It's like, nah, that's not average. 3 is not the average. 50,000 different species. You eat way more than that in lifetime.
I'm not always splendid.
Second derivative test. SDT. Okay. Second derivative test will have identical type of calculation. We are going to partition on points that we calculate, on vertical asymptotes. If there are no such things, the whole thing is one partition. Calculation stays the same, except all of the derivatives now are swapped with the second derivative, right? So nothing will change other than concept of what you're getting out of it, right? So that's why we have next thing. So remember how I started with the applied problem? Let's talk money. Let's talk money again. You want to invest money into market and make some money. So these are the 3 portfolios that are presented. The question is which one you invest into. So they all have money on the y-axis and time on the x-axis, because the money is grown or lost in time. And here are the options. You are investing, let's say, $100 each time, or 1,000. So that's the same, right? And look at the graphs. Usually my first question is, which one of these makes money in time? Which one of these makes money in time? And the answer is all of them, right? Do we all see that they are ending with a higher value to the right? They're all increasing. They're all going to make you money. Now the question is, are they all equally good?
No.
And the answer is no, exactly.
Second one.
Which one is the best? Second one, exactly. Second one is exponential growth, right? So if you continue another day, the third one is not going to make you any more money, maybe another 3 cents, right? The third one. The first one will always be linear. It always makes the same amount of money every day. But the second one takes off, right? And it keeps making more and more and more and more, right? That concept that you see there, right? Where all of these are increasing, that concept there is called concavity. And this is what we get from our second derivative, right? So second derivative will measure how fast is the first derivative changing, right? Well, that's acceleration and velocity, right? So your first derivative is velocity, and then acceleration is change of velocity. So now concavity is a change of increase and decrease. So, right, if 2 people are gaining weight, right? 2 people are getting fat at the same time, right? One who eats more cake will get fatter more, right? I mean, they're both getting fat, right? But one is going to... So you can go now across the board and find where these further fit the narrative we have. So now I'm going to say over here, no concavity. This is called concave concave up, and this is concave down. And again, please note that all three are increasing. All three are going to make you money now. And they all have, you know, they all have their advantages in the market. This one is stable. So if you invest in something that, you know, you just don't want to worry about, this is the high risk one. They are very rare. But if you hit that jackpot, you're done. Like my friend who lives in Maryland, right? So this guy seeded money out of high school, like in many places, because you just need to hit one of these, and he hit one of those, right? So now, 3 houses, the $1 million house in Maryland, with 12 cars, right? He can do whatever the hell he wants, right? Because he hits a jackpot, right? And then this one, right? If you know that you can make something extremely quick, and then you're just going to quit it because over time it's not going to work well. But on a very short run, right? You have some insider information that something is going to happen. This is just quick and it's like pull out, right? So they all have their advantages, right? They all have their advantages if you're talking market. But the one that's going to make you the most money over time is the one that it's concave up in this case. So this is what we have for the second derivative test. We have the concept of concavity, and the test goes the same way as the first test goes. If the second derivative on f double prime of c is on AB is bigger than 0, it's concave up. If it's less than 0, it's concave down. And if it's 0, you have inflection point. So instead of critical point, you have inflection now. So let's write. And the calculations and everything is the same. So if second derivative computed at c is bigger than 0 on some interval a, b, then f of x is concave up on interval a, b. If second derivative of c is less than 0 on a, b, then f of x is concave down on AB. And finally, we get to see that third mysterious point. If f double prime of c is equal to 0, then x equals c is what we call an inflection point. Now, what is the inflection point? I'll point the arrow to it and quickly describe it. Inflection point is point where change of concavity occurs. So you have seen this point many times, and let's do it now. Y equals x cubed. So x cubed has the point of inflection. What do we have? Y prime? No one cares, right? It's first derivative. So 3x squared. We need it so we can get to the second one, right? Let me switch the notation to f. Is 6x. And as I said, guys, identical calculation. Set it equal to 0 to calculate inflection points. So x equals 0, and that's your inflection point. To do the second derivative test, we partition on the entire domain, in this case negative infinity to positive infinity. We partition at the inflection point, and we pick C, test point C again, test points C, we pick this, we pick these, there we go, and now second derivative computed at -1 is going to be 6 times -1, which is -6, which is less than 0, which is concave down. Boom, CD. Second derivative, 1 equals to 6 times 1 equals to 6, larger than 0, concave up. There we go. Perfect. And now we write the answer. Remember, answer is important. On this answer, we say f of x is concave down on -∞ to 0. F of x is concave up on 0 to infinity. This is your answer. Just to, see if this makes sense, I am going to graph x cubed because I know what that graph looks like. Do we see a concave down piece here? Answer is yes, because concave down piece is like a downward opening parabola that would spill the water. Concave up piece. Concave up piece, remember how fast it grows to pick up the money, right? So concave up piece, see, you can complete that into... So concave up shows up as a U, shows up as these two separate pieces also, a piece like this or a piece like that. So these are the three cases of concave up. And then concave down is going to be this. So these are the shapes. And, you might want to box that, put it on a cloud or something to know. Let's take a look at spicier cases, right? Concavity. No. Yes, okay. Let's see something that... remember, we have to take the second derivative, right? To get there. Otherwise, it's the same calculation. So let's start. We haven't done any ln's, right? So we can do either 68 or 69. 68 has a product. 69 has no. Let's do 69 because no product rule, so it's easier. Faster. So f of x is equal to ln 3x squared plus 1. We need the first derivative, which is copy the function as is and put its derivative on top. And now for the second derivative, we have to do the quotient rule, let's say 3x squared plus 1 in denominator squared. 3x squared plus 1 times the derivative on the top is 6 minus 6x times the derivative on the bottom is 6x. Great. There we go. So when we simplify this, we have 18x squared plus 6 minus 36x squared divided by 3x squared plus 1, everything squared. Now, the denominator doesn't bother us because when we set it's equal to 0, it's going to multiply into 0 and die. So we'll just worry about the numerator in this case. This is going to be 6 minus 18x squared divided by 3x squared plus 1 everything squared. And we set this equal to 0. That's our gig, right? So we get to solve 6 minus 18x squared equal to 0, which is 18x squared is equal to 6. And x squared is equal to 1/3, right? We can divide by 18, divide 6 and 18, right? So it's 1/3. X is equal to plus minus square root of 1/3, which is plus minus root 3 over 3 if you rationalize, right? Let's say you care, right? So that's the one you get. Great. So we could ignore the domain and then just find the hard way, right, where the domain is. Or we can argue and see if we have all of these things at the same time. Yes.
I have 2 problems in the conference center.
All right. I'll be right down.
Okay, thank you.
You're welcome. So, the domain of this problem, guys, right? The domain of this problem is going to be all real numbers in this case. You know that that the ln has, right? ln has only positive side. But because there is x squared, right? That's going to allow for all of the negative numbers to come in because it's squaring it, right? So I will ask you to, I'm just going to run downstairs and fix the issue with the computer. We now know that it's from negative infinity to positive infinity, and we have the 2 partition values, negative root 3 over 3 and root 3 over 3, right? Those are our values. You can find the decimal values for these numbers in the calculator. And then obviously pick the 0 in the middle, and then on the sides pick -5s or negative whatever, right? And plug them in a second derivative in a compute, right? For concave up, concave down. I'll be right back just to probably just control P. Actually, you want. You want to go? Bring your walk. You can leave the bag.
still.
All right.
Most popular thing. Did you try to reboot?
All right, so 0. And we can use -1 and 1. Now, second derivative, computed at -1. 6 minus 18, -1 squared. Divided by 3 times -1 squared, plus 1. Everything squared. Do I care about the denominator? No, it's squared. It's always positive, right? So I have 6 minus 18 in the numerator divided by a positive number. This is negative divided by a positive. That's negative. Let's can't fit equal. That's negative, which is, well, let's do it this way. I want to fit in same. So that's negative. So the whole thing is negative, which is less than 0. So concave down on the first one. F double prime at 0. 6 minus 0 over a positive number. It's positive divided by a positive, right? So concave up, larger than 0, right? Concave up. And finally, second derivative for 1 is the same as the up one, right? Because it's 1 squared over, again, put positive there. So that's going to be a negative divided by a positive, less than 0. So we have a concave down. So, no, answer. I almost forgot. So this is the answer you're providing for tests. Let's say you're interested in points, right? You put this one down. So f of x is concave up. And then we just take a look from -√3 over 3 to +√3 over 3. F of x is concave down, -infinity to -√3 over 3, union √3 over 3 to +infinity. And you box it. So this is what we have for our answer. We are giving the x intervals, x1 to x2. I said a and b, right? So we are giving x intervals to get the value. All right. Next example, and we take a break for lunch. Should we do a trig question? This was ln question, right? Yes, this was ln question. We can do a trig question. We can do exponential. What should we do?
Trig.
Trig, huh?
Yeah.
It sounds good. Fine trig. There it is. 2 cosine 2x. Excellent. So f of x is equal to 2 plus cosine 2x. And this is question 74. And we are on 0 to pi. That's where they chop the domain. Again, cosine is going to go to infinity, right? So they just cut it off. What do I have? First derivative? -2 sine 2x. Excellent. Do we need? No, right? We want the second derivative because we are working on a second derivative test. And that's -4 cosine 2x. And this is the one we set equal to 0. When you divide both sides by -4, it's gone. So cosine 2x equals 0. So where is the cosine equal to 0? It's equal at pi over 2 and at 3 pi over 2. So 2x is equal to pi over 2, and 2x is equal to 3 pi over 2. When you divide by both sides by 2, you get pi over 4, and over here you get 3 pi over 4. Both of these values are in 0 to pi, so we're good to go. No asymptotes, right? No VAs, because it's a cosine. And we are chopping off the domain 0 to pi because the problem wants us to. And then I have a partition at pi over 4, and then I have another partition at 3 pi over 4. So now I need to pick the test points. So I'm going to pick pi over 8, because when I plug that in, the 8 and 2 will cancel. It's nice. Over here we can just pick pi over 2. And then this is going to be, so 3 times 2 is 6, so 7 pi over 8 over here. Because pi is 8 pi over 8, right? So one before that would be 7 pi over 8. And now we take our f prime, double prime of pi over 8, which is negative 4 times cosine of 2 times pi over 8. This is negative 4 times cosine of pi over 4. Now cosine of pi over 4 is root 2 over 2, but I don't care because this is a negative times a positive. That's going to be a negative, it's less than 0, so concave down. Next one is what? Pi over 2. So that's going to be negative 4 cosine of 2 times and then pi over 2. Well, 2's cancel. So it's negative 4 cosine of pi. Now, cosine of pi is negative 1. So I have a negative times a negative. And that's going to be a positive, larger than 0. So concave up. And finally, 7 pi over 8, negative 4 cosine of 2 times 7 pi over 8. And that's going to be negative 4 cosine of 7 pi over 4. Now this one we'll have to take a look at the unit circle. All students take calculus, right? We put that for positive negative values, and divide all of these into quarters. So 0, 1, 2, 3, 4, 5, 6, and 7. So cosine of pi over 4 is the same as the cosine of 7 pi over 4, which is a positive value. So negative times a positive is going to be a negative number, less than 0. So concave down. Now we all know that everything concave up, concave down, increase, decrease for cosine signs, they alternate quickly, so it's okay. But we calculated all the way. All right, so now we have to write the answer, right? So answer is, what is the answer? The answer is f of x is concave down on 0 to pi over 4 union 3 pi over 4 to pi. F of x is concave up on pi over 4 to 3 pi over 4. And we put the box around that, as that is our answer. Great. Let's do one more since we have time. Now again, I did different problems in my other section. So if you watch the other one that it's not labeled as Calc1s, you can see other examples. They're also from the book, it's just different numbers. I think I did 87, so let's do something else. How about, let's do 84 because it looks crazy already with e to the x over x plus 1. Right? So why not, right? Oh, let's take quick derivatives. You know how to take a quick derivative? You circle this in your notes, and then you push the math button. Hey, come on, this needs to be e to the x. E to the x as the exponent. So you circle this in your notes and you push the math button. There we go. And then in the pull down menu here you say differentiate. That's how, right? So, you know, do that in your notes. And now for the second derivative, right, you circle this one. Like that. You push math and you say differentiate. So differentiating is very easy. And now you set this equal to 0. So what do we have? Well, denominator multiplies into 0 and just dies. So I have x squared plus 1 equal to 0 and e to the x equal to 0. No solution on any of them. No solution on any of them because x squared is going to be equal to negative 1. You take, right, you get positive negative I, and e to the x, they don't intersect. So, no solution, no solution. Meaning, no inflection. But look at the top problem, guys. What do we have? We have vertical asymptote at x equals to negative 1. So that we will be partitioning there. Again, if we didn't have vertical asymptote, we can still just use everything as one partition. But we have the vertical asymptote, so we have to be careful about that. So now, second derivative test. Partition at negative 1. And we have our negative infinity and our positive infinity in our domain. Test point picks 0 and negative 2, whatever. So we have our second derivative test at negative 2. It's negative 2 squared plus 1 times e to the negative 2 divided by negative 2 plus 1 cubed. All right, so I have a positive times another positive divided by a negative for a total of a negative, which is less than 0, which is concave down. So you have 4 plus 1 is 5, and then e to any exponent is always positive because e graph is always above 0, right? So you don't have to worry about e at all. It's always positive. And then you have the negative 2 plus 1. See, it's cubed now in denominator, so I can't claim positive all the time because cubed. So the cube, the odd exponents always preserve the sign. Even exponents always give positive. So we have the, right, all of that is there. And now I'm going to have the other calculation with 0. So f double prime at 0 is going to be 0 squared plus 1 divided by 0 plus 1 everything cubed, and then e to the 0, right, which is 1. So that's a positive times a positive divided by a positive. So So all positive, larger than 0, concave up. Answer. F of x is concave down, negative infinity to negative 1. F of x is concave up, negative 1 to infinity. And you box that because that's your answer. So, you know, the problem is 10 points. This box is 2 points, right? It's 20% of a grade for that problem. It's a big deal, right? 20%. Now, why is it so much? Well, because, guys, when you start working, report is what people read. They don't care about your calculations. If they knew how to do calculations, there would be no need to employ any one of you. Or if they had time to do the calculations by themselves. Let's say they know, right? So, you as an expert, go in and you do your calculation. Financial analysis, whatever the hell the job is, right? And you are writing the report, right? So, this is what's in the report. None of this stuff is included. None of the steps. No one is checking your work, no, right? Because you're supposed to be expert. You're paid, right? If you keep messing up, every time it's wrong, out, right? Next person. So, the sentence answers that we have, right, are the answers. And the rest, right? Well, sure, it's education, so, you know, if you mess up on the minus signs, the partial credit and all these kind of things. But no one cares about anything else other than this box. Like, that's the only thing that's important. Great. So we're going to take. Oh, actually, wait. No, we still have time. What I was thinking is let's start the next lesson, and then we'll. Let's start the next lesson, and then we'll take the lunch break, and then we'll finish the next lesson, and then go home for lunch on 2. So the next lesson, because it's still early, it's nothing there. Let's do the 4.4 graphing functions by hand. I want to put the shopping list up, and we can do the very basic introductory example. All of that goes quick. 4.4. So actually, hold on.